Welcome to our stats lecture covering 10.5, which is a review of chapter 10. So in chapter 10, we saw hypothesis testing for both proportions and means. In these next few problems, we're going to have to identify what type of question we're looking at by identifying what parameter we're testing a claim on. The Tennis Industry Association reported that 41% of tennis fans were female. In a sample of 30 tennis fans, 15 were female. Do the results suggest that the percentage may have changed? Use alpha equals 0.02. So the fact that we're talking about this test for proportion. Which means both of our hypotheses are going to be statements about P. The null value is going to be that reported value of 41% of tennis fans, and we're going to convert that to a decimal, so P equals 0.41. The claim is whether or not this percentage has changed, so the alternative is going to be P is not equal to 0.41. Step 2, we state our level of significance. In this case, alpha equals 0.02. Step 3, we calculate our test statistic. The formula for our test statistic when we're testing a claim about proportion, Z equals P hat minus P divided by the square root of P times Q over N. Anytime we're making or performing a test on proportion, we're going to use a z-test. On the other hand, if we're testing a claim on a mean, we're going to use a t-test. P hat is our sample proportion. There were 15 out of 30 in our sample that were female. P is our null value, 0.41. Q is found by subtracting P from 1. Q equals 0.59. N is our sample size. We had 30 people in our sample. Substituting these values in, Z equals 0.50 minus 0.41 divided by the square root of 0.41 times 0.59 divided by 30. Make sure you're really careful when you enter these values in and you put the P hat where the P hat goes and the P where the P goes. Our test statistic, we're going to round to 2 decimal places, which comes out to 1.00. Step 4, we begin by identifying the type of test. And that's given, or we determine that by looking at our alternative hypothesis. Since our alternative is P is not equal to 0.41, that makes this a two-tailed test. For this example, we're going to go through both the critical value method and the p-value method. For the next 2 examples, we'll just go through one of those methods. The critical value method we know is based on alpha. In this case, because it is a z-test, we're going to use inverse norm to find our critical value. And to make our decision, we're going to compare the critical value to our test statistic. So we set up our diagram to model a two-tailed test. The area in our 2 tails represents our rejection region, and the total area of the rejection region is equal to alpha. So in this case, 0.02. Since there are 2 tails, we divide that by 2, and we get 0.01 as the area in each individual tail. Using inverse norm on our calculator, the area to the left is 0.01. Our critical values are negative 2.326 and positive 2.326. Now on this same figure, we're going to mark our test statistic, which is 1, which is going to be about here. Because our test statistic lies outside of the rejection region, our decision is fail to reject the null hypothesis. The p-value method is based on our test statistic. Because this is a z-test, we're going to use normal CDF. And to make a decision, we compare our p-value to alpha. So we have our two tails, and using a different color, that the tails now represent our p-value. The right tail is bounded by our test statistic 1.00, and by symmetry, the left tail is bounded by negative 1.00. Using normal CDF, we can find the area of just one of these tails. By giving our lower bound and upper bound. The lower bound for this right tail is going to be 1. So the lower bound is always our left bound, the upper bound is our right bound. So our lower bound is going to be 1, and our upper bound we're going to use positive 100. The mean is 0 and the standard deviation is 1 for our standard normal distribution. So that area in just the right tail is about 0.1586, and that decimal continues. So our p-value, to find that, we're just going to multiply that value by 2. But we're going to multiply the answer that's in our calculator, not any rounded values. So our p-value is 0.3173, rounding to 4 decimal places. Comparing this to alpha, our p-value is significantly larger than 0.02. So we make the same decision to fail to reject the null hypothesis. In our fifth and final step, we state our conclusion, which is explaining our decision in the context of the problem. Since our decision was fail to reject the null hypothesis, then there is not enough evidence to support our claim. And the claim was that the percentage of female tennis fans have changed. Percentage of female tennis fans. Nationwide, the average salary of actuaries who achieve the rank of fellow is $150,000. An insurance executive wants to see how his fellows compare to the fellow, or how this compares with the fellows in his company. He checks the salaries of 8 fellows and finds the average salary to be $155,500 with a standard deviation of $15,000. Can he conclude that his fellows make more than the national average using alpha equals 0.05? So we have a claim about the amount of money they make. We're talking about averages. So this is going to be a hypothesis test for the mean. One other observation we might want to make is that we have a small sample size. So if we were to see this problem on MyStatLab, we may have to verify those normality requirements that we talked about in section 10.3. The first step, we identify the null and alternative hypotheses. And those are both statements about mu. The null value is going to be the nationwide average, which is $150,000. And the claim is that the fellows at this executive's company makes more than the national average. So we're going to claim that the mean is greater than $150,000. Step 2, state your level of significance. Alpha equals 0.05. Step 3, we calculate our test statistic. The formula for the test statistic when we're testing a claim about the mean is T equals X bar minus mu divided by S over the square root of N. Anytime we're testing a claim about the mean, we're going to use a t-test. X bar is our sample mean. So our sample of 8 had a mean of 155,500. Mu is the null value, so 150,000. Our sample standard deviation is 15,000. And our sample size is 8. With these particular values, be very careful that you have the correct number of zeros and the correct number of fives. We're seeing a lot of similarity between X bar, mu, and S. Substituting those values into the formula for our test statistic. When we type this into our calculator, our test statistic comes out to 1.04. Step 4, we begin by identifying what type of a test we have. In this case, we have a right-tailed test. And we're going to use the critical value method for this particular test. Again, we know that the critical value is based on alpha. Because this is a t-test, we're going to use inverse t to find our critical value. And to make our decision, we compare our critical value to our test statistic. Setting up our right-tailed diagram, the area in our right tail represents our rejection region, and the area of our rejection region is equal to alpha, so 0.05. When we use inverse t on our calculator, we need to give the area to the left and the degrees of freedom. So the area to the left of my critical value is 0.95. And the degrees of freedom are always n minus 1. So n was 8. So our degrees of freedom are 7. Our critical value is 1.895. Comparing this to our test statistic of 1.04, 1.04 lies over here, which is outside of the rejection region, so our decision is failed to reject the null hypothesis. Our conclusion will begin, there is not enough evidence to support the claim. And our claim was that the fellows in this executive's company makes more than the national average. The average red blood cell count for women is 4.8 million cells per microliter. A sample of 50 women is obtained, and each woman's red blood cell count is measured. The sample mean is 4.61 million cells per microliter, and the sample standard deviation was 0.54 million cells per microliter. Use a 0.01 significance level, so that's alpha equals 0.01, to test the claim that the sample is from a population with a mean less than 4.8 million cells per microliter. So there are a couple different phrases within this problem that indicate that this is dealing with the parameter of mean. Another indicator that we can look at is if we're given values of mean and standard deviation, those variables aren't used in any of the formulas when we're dealing with proportions. So that's a pretty good indicator as well. Our first step, we state our null and alternative. These are both going to be statements about mu. The null value is at 4.8. And we don't need to add the units here, but when we write our conclusion, we will make sure that we include those. The claim is that the mean is less than 4.8. Our level of significance is 0.01. Again, the formula for our test statistic when conducting a hypothesis test for mean is a t-score, and it equals x bar minus mu divided by s over the square root of n. X bar is our sample mean. In our sample of 50 women, the mean was 4.61 million cells per microliter. Mu is our null value, which is 4.8. The sample standard deviation was 0.54, and our sample size was 50. Using our calculator to evaluate this, our test statistic is t equals negative 2.49. Now, before we go on to step 4, I want to make one quick comment. In this particular test, we have a left-tailed test, and our test statistic is negative. If we look at our previous example, we had a right-tailed test, and our test statistic was positive. Now, this should make sense because our claim, it needs some sort of evidence. In order for this executive to say that he thinks his fellows make more, he has to have some sort of evidence that states that. So his sample has to support that claim. Now, the point of the hypothesis test is to determine if our sample is enough evidence, but it should still support that claim. It wouldn't make any sense for him to say, oh, I think my fellows make less than the national average when his sample is saying that it is more. So again, your test statistic, the sign of your test statistic, should align with what type of a test you have. Now, this doesn't apply as directly with a two-tailed test because we do have two tails. So it could be more or it could be less. So the sign is not definitive based on that type of test. Step 4, we make our decision. So this is a left-tailed test. And I'm going to use the p-value method for this example. We know that the p-value method is based on our test statistic. Because this is a t-test, we're going to use t-CDF to find our p-value. And to make a decision, we compare our p-value to alpha. So we're setting up our diagram for that left-tailed test, and the area in our left tail is our p-value, and that left tail is bounded by our test statistic, negative 2.49. In order to use the function TCDF on our function, we have to identify the lower and upper bounds and the degrees of freedom. The lower bound is your left bound, so over here we're going to use negative 100, and our upper bound is the right bound, which is negative 2.49. And the degrees of freedom is our sample size minus 1. Our sample size was 50, so the degrees of freedom are 49. So our p-value equals 0.0081, which when we compare that to alpha, 0.01, our p-value is less than alpha. When our p-value is less than alpha, our decision is to reject the null hypothesis. Because we're able to reject the null hypothesis, that indicates that this is enough evidence to support the claim that the average blood cell count for women is less than 4.8 million cells per microliter. The homework for section 10.5 is optional. We encourage you guys to do it to get another dose of practice for identifying what type of a parameter you are testing, and that way you use the correct formula for the test statistic and the correct calculator functions.